Welcome back to the restoration of this MZ-80K. This time we have a long episode, the longest so far, and we will restore this analog video board. Most of this video will be about what I call preemptive offline troubleshooting, when I go over the entire board with a multimeter without power connected, just preemptively checking for all the components, especially the semiconductors. But to start in a good mood, of course, I recapped the entire board. So I'll start with a short 2 minute something time lapse of the recapping process, or half of it. And then I will come back with the troubleshooting. Enjoy. Now you will notice that I'm doing a lot of stuff before I even turn the computer on for the very first time. And the reason is this restoration stuff needs to be done anyway. And chances are that some of the defects or problems that would lead you to a wild goose chase in troubleshooting anyway may disappear just because of the restoration work that needs to be done in any case. So that's why I do it first. I will repair this machine one way or the other. It doesn't have custom chips that are impossible to find. So it's a matter of time. So that's why I do the restoration before I even turn the computer on. And a lot can be accomplished with the computer off, including this offline preemptive troubleshooting, so to say. You go over an entire board with your multimeter in continuity mode or diode mode, and you check the semiconductors, you check the traces that look suspicious, you check the value of some resistors and capacitors in circuit if you can, the ESR. A lot can be done, but you need to follow along on the schematics in order to be able to interpret your readings, because you're doing in-circuit readings. So what I'm going to do now is just take you along the beginning of this process live. I will come back to offline commentary shortly, but at least to give you a sense of how I go about it. I don't know whether it's the best way to go about it, but it's my way. The important thing is that 12 volts is not ground, because otherwise there would be a short. Yeah, 12 volts is okay. Then vid is the video signal, not shorted. Then sync, not shorted. And then sound in, also not shorted. So okay, this is okay. There are no shorts on the video board, as I was suspecting, at least not after I recapped. So let's do other tests now. A simple test is to look at this large 2-watt resistor. It's all red and it has 2.2K. So we can just measure this one to see if it is 2.2K. Although it is in circuit, yeah, 2.2K. So this transistor is just, sorry, this resistor is just fine. 2.2K resistor. Let's look at some diodes now. There is a diode here, D2007. Yeah, goes from the flyback via 40K ohm resistor to ground. So let's check this one. Diode mode, it's polarized from this side to this side. Should have a voltage drop. Oh no, I'm putting it wrong. Okay, so this should have a high voltage in circuit because that's the non-conducting direction of the diode. And you see the voltage keeps rising, so I'm charging some capacitor somewhere there. Yeah, this is much more than the breakdown voltage of the conducting voltage of this diode. Now this is the correct polarization. Now we should have about 0.5, yeah, 0.453, yeah, that's okay, that diode is okay. Diode 2005 is in parallel with a bunch of capacitors and one side is ground. So let's check which side is ground. Okay, it's not this. Yeah, this side is ground. And it should conduct from the ground side. So polarized this way, it should give us about half a volt voltage drop. It's charging the capacitors here next to it in parallel. So this should stabilize at around half a volt, 0.4 something, 0.4 high. Capacitors are still charging. Yeah. Okay, now that's the true voltage drop across this diode. The other way around, it should be a much higher value, but there will be also capacitor charging in the process. So it looks like this diode is an open circuit, but I guarantee you, yeah, it's not. So now that the capacitors are discharging, we will get the proper value. It should be more than the other way around. Yeah, this is just the capacitors. So this diode seems to be okay. There is a transistor here. It's a PNP transistor. It's very handy. I see the markings already there. So we should observe a voltage drop from emitter to base of about 0.6. Yeah, that's correct. And then from collector to base the same thing because it's PNP, 0.6. Correct. And the other way around, if this was not in circuit, we should get a over limit. But because it is in circuit, we should just observe a higher voltage. Yeah, 2.7, and collector to base, or base collector. Yeah, so this is okay too. Now look at what could happen if you do not have the schematics. I'm looking at this transistor Q2005, the emitter is connected to ground. I just verified that. And now I'm going to look at the voltage drop between base and emitter. And look, it's 0. It's like there is a short there. Whichever orientation I check that voltage drop, I get 0. So I go to continuity mode, and they are connected. So is the transistor defective? Do I have a short circuit between base and emitter? Of course not. Look at the schematic diagram on the lower right. The base and the emitter are both connected to a little transformer, T2001. And of course, if you're connected to the winding of the transformer, you get full continuity because the circuit is off. It's an offline measurement, and the transformer will behave as a short. But of course, the transistor is just fine. Nonetheless, I will change the 3 semiconductors that work the hardest, including this transistor we just checked, because this is a restoration, not only a fix. I will also change that IC that you see there from the back. That's the vertical driver, has a big heatsink, works very hard. And I will also change that little power transistor over there. It doesn't have a heatsink, but also works hard. These are 3 common points of failure, so I'll replace them all. Before I do that, however, there are some odd jobs, like taking away that switch on the 12-volt line that the previous owner added to alternate between the internal monitor and external monitor. I'm getting rid of that switch and connecting the 12-volt line of the flat cable straight back to the main PCB. I will make a mistake, you will see shortly. I'm also putting some heat shrink to reinforce that cable so it doesn't have to take much mechanical strain. So there it goes. I just soldered it in, and now I'm going to reflow the solder joints of all the other wires in this flat cable. This is the cable that brings the signals from the motherboard to the video board. I'll reflow them all because I also plan to put some hot glue to relieve mechanical strain. And so that's my chance to do that reflowing. Now I discovered I made a mistake. I put the 12-volt wire the other way around. Mechanically it was not very handy, so I flipped it, and now I'm soldering it back in again, cleaning the flux. And then I think I will just tie that 12-volt line back to the flat cable with the other signals in it, just like it was originally. And I'm using some electric tape to do that. That's also for mechanical stress relief. Cleaning the connector that goes into the motherboard with a flush action 2-step contact cleaner. Also the little connector that goes into the back of the CRT. I then check for continuity between the connector that goes into the motherboard and what's arriving on the video board, because again, I'm going to put hot glue in there to relieve mechanical stress. So that's my chance to do it, to make sure that everything is working fine before I commit to that. So there comes the hot glue, and now those cables are not going to be pulled out very easily. They can be pulled out, but the mechanical stress will be vastly relieved. I'm also putting contact cleaner on that other little connector that goes to the windings of the yoke of the monitor, of the CRT. They're very dirty, as you can see. That's my chance to clean them and prevent going into a wild goose chase if the CRT doesn't work well just because of bad contact. Now I'm removing that extra volume control potentiometer. I will remove that shortly as well. What am I removing right now? Let me flip the board back so I remember. That's the volume control wires that are going to that extra potentiometer the previous owner put in there. I'm taking that away. I will connect the speaker cables straight back into the board, the video board, like they were before. I'm also removing something else. Let me flip the board so I remember what that was. Oh yeah, I'm removing one of the 3 semiconductors that I wanted to change. I'm taking that away as well, that little power transistor. Off it comes. And I'm replacing with this, a modern equivalent. I glued with thermal glue a little heatsink at the back as an abundance of caution. But this is a higher rated modern replacement for that power transistor. I'm cleaning the board under that power transistor and around the connections for the speaker cables. That's my chance to do that. adjusting the leads of the transistor, and in it goes. Some flux, some soldering for good measure. And of course I always use a solder fumes extractor because I want to live long and prosper. Cleaning the excess flux. And these are the speaker cables. I removed that extra potentiometer, that modification, and now I'm just exposing the metal, tinning them with some flux and solder, and I'm going to insert them back into the motherboard, into the video board where they belong. I added a little heat shrink there also to relieve some of the mechanical strain and keep those two wires together. Soldering them in now. I'm just tacking them first while pushing them into the board to make sure they sit flush. And now I finished the soldering job and cut the excess leads and clean the flux. So now the heat shrink goes back down, and with a heat gun I shrink the heat shrink to keep those wires together and relieve some mechanical strain. Now the vertical driver, I'm going to replace it with this one. It's a better, a newer version of the same chip. It's new old stock. That vertical driver is a very common point of failure, so I'm not going to even test it. I'm going to remove it. The new one has a different size, as you see there. It's smaller, but it can be fitted in if I put a socket to elevate it a little bit, and it can be affixed against the heat sink with some washers, as you're about to see. So that's the desoldering process of the old vertical driver, which is probably working still as far as I know. Of course, I will keep it in my stash of old parts. Off it comes. You see, it's a much bigger part, but it is possible to fit the newer, smaller one very cleanly without having to drill any new holes. I'm about to show you how that can be done. And the newer part is better anyway, and it's new old stock, so it should last a lot longer. Again, part of the restoration, you don't only fix problems, you eliminate future points of failure, likely points of failure in the future. So I didn't have a linear socket, so what I'm going to do, I'm going to destroy a 40-pin dip socket, precision socket. Normally I don't do this, but I ran out of my little single row sockets. So there goes that little strip, which will work as socket. I'm using now some blue tack to make sure it is in place while I solder it, because it's right under the heat sink. It's difficult to hold it with the finger. Flux goes in, making sure it's really flush. And I'm not completely blind, but I don't have good vision, so I like to use a magnifier so I can see the wetting action as I'm soldering, and I know that the soldering job is properly done if I can see the wetting action. That's why I use that magnifier so often. Now I'm using those washers to press the IC against the heatsink, and I'm using also lock washers to make sure that the pressure is never less over time. That's thermal paste to make sure there is good thermal contact with the heatsink. And there go the little nuts with the washers and lock washers, so the pressure is maintained over the years and the heat transfer maintained as well. And now I'm just going to clean the excess thermal paste. Nobody's ever going to see this, but I know it's there and I want it to be neat, so I clean it out. And that's the end result. You see, I'm using the original holes of the heatsink, but not the holes of the new chip. Instead, I'm using a larger washer under the screws to press the top of the new chip against the heatsink with thermal paste in between, and the little socket underneath to elevate it so the washers do their job. This is as good as the original one, if not better, because I'm using thermal paste and originally there was none. Now, before I continue, I forced myself to clean the potentiometers that adjust, vertical hold, horizontal hold, brightness, contrast, and so on and so forth, volume. They were very, very scratchy, so I'm using high quality flush action two-step contact cleaner and exercising them a lot by turning the knobs to make sure that they are clean. I could replace them as well, but these are mechanical components that if they are clean, they work just fine. So I rather keep the originals already fit into that little board. I spent quite a lot of time doing this to make sure it's properly done and that the knobs turn very smoothly and are not scratchy anymore. We clean out the excess of contact cleaner. All right, what do I do now? I have to watch it with you because I no longer remember. I'm just showing you the victims of the day. That's the end of the day for me when I was shooting this. So that's the old vertical driver, that's that little power transistor, which we've replaced with a new one. And this is the volume control potentiometer. It was a modification. That's gone. It doesn't belong there. I'm going to close the hole anyway in the case that corresponded to that. I'm putting a dab of hot glue on some of the larger capacitors and the connections to the audio cables, again to relieve mechanical stress. And that was the end of the day for me. The next day I came back and I replaced that other transistor that I showed you. You know, if you would measure it in circuit, you would think it had a short. It didn't. I'm going to try to show you that it doesn't have a short when it's off circuit. I'm using a little desoldering pump, very cheap, because I didn't want to wait for my desoldering station to warm up. And those little hand pumps are more than enough if you only have a couple of pins. Together, of course, with desoldering wick, which is the best thing under the sun. It's a pity people don't use it more. So after it's desoldered, only then I remove the screws, the bolts, to not put mechanical stress on the bolts. I'm trying to show to you now that it doesn't have a short, but because of the glare on the screen of the multimeter, you can't see that. Believe me, the transistor didn't have a short, and on the board it still looks like it has a short because of that little transformer that is on the board. If you're measuring it for continuity across the windings of a transformer, it will look like a short circuit, but it's not. Now I'm cleaning the heatsink very well because it's important for thermal conductivity that there is no oxide in between, because oxide can be a thermodielectric, it can be a thermoinsulator. So that's clean. I also clean the new parts, the transistor, and I put some thermal paste for optimal thermal conductivity. These little simple things that were not done in the original, it can be the difference between a transistor working for 20 years or 40 years. So I do it, removing the excess thermal paste now, and you will notice that I will put the nuts back before I solder, because I don't want the solder joint to take any mechanical stress. Now I forgot to add those lock washers. There they are. And that will make sure that there is good pressure over the years between the part and the heatsink for optimal thermal conductivity. And only now I'm soldering it in, so the solder joint will take no mechanical stress. Whatever mechanical stress there will be taken by the nuts and the bolts. And I think this concludes it, or not. Yeah, I think that's it, except for some cleaning. Oh, I know what's missing. One of the capacitors I didn't recap originally because I didn't have it. It was a bipolar capacitor that's not very common. So I had to order it. It came in now. So now I'm adjusting the leads to put it in there, but the holes on the board were too small for this new capacitor. I'm going to widen the holes just a tiny little bit with this tip on my Dremel. A very tiny increase in the diameter, and if you look at the holes, it didn't destroy the pads at all, it didn't damage even the pads at all. And now the new bipolar capacitor will fit in, but what I will do, I will put hot glue first, right underneath the capacitor, because that particular capacitor is exposed to large and high frequency oscillations, so that could induce vibrations. To avoid that, I put the hot glue first, and while the hot glue was still hot and malleable, I pressed the capacitor in and waited for it to dry a little bit. You see the hot glue there squirting from the bottom of the capacitor? It's now relatively dry, so only now I proceed to solder the new capacitor in. And I use this knife, this blade, to remove the hot glue, because the leads passed through hot glue. So to avoid having a dielectric there, I use that blade and I clean it and use the blade again to make absolutely sure that the leads are exposed and not dirty with hot glue. Then I put the flux and I solder it in. And I think that concludes it for this episode. It's time to see the end result. And next time we are going to see what can be done about this odious keyboard and also restore the cassette deck. So it's a double whammy next time. Until then, take care and I'll see you soon.